STS-27 was my third launch, and it was only the second launch after the Challenger accident. Well, I will never forget, we maneuvered the arm, and Mike Mullane was my arm operator, so he moved the arm over there, and we brought up the television image of the right wing, and I looked at what I was seeing, and I said to myself, we are gonna die.
Getting troops and equipment through the air and quickly on the ground and into combat. This was a challenge tackled in World War II with the use of gliders like the Waco. However, gliders were built to be expendable and could not be returned. They also had to rely on another powered aircraft for towing. A major problem for glider pilots was that they only had one chance at landing. This meant that they could not avoid obstacles unseen from the air, or even deliberate traps set by the enemy. Many glider troops never even got to battle. They simply perished in their vulnerable wooden hulls. Sometimes the means of arrival was even more deadly than the enemy, and this was equally the same for both sides. Early in the war, the Germans produced the Gotha 242, a fairly successful glider that used a twin-boom tail arrangement. The 242 could carry a useful payload, which would be quickly unloaded through a large rear door. Some of the Gothas were fitted with small French piston engines, which negated the need for a tow plane. However, the most important feature of the powered glider was that its pilot could choose exactly the best place to land without running out of height. It also meant that after unloading, the aircraft could quickly take off and return to its base for another mission. This is the U.S. Air Force's Fairchild C-123 provider. Much like the Gotha 242, it was originally built as an unpowered assault glider. Then later, engines were added. However, the glider version was nothing like the wooden Wacos and Gothas used in World War II. This aircraft was big and made entirely out of metal, and was also heavily reinforced for crash landings. If American soldiers had to glide to war again, then their safety was going to be a major consideration. Only 2 of the giant glider versions were built prior to the whole unpowered flight program being abandoned. However, the motorized version did go into production, and over 300 were successfully deployed. The provider was very robust and able to cope with short and primitive landing areas. However, it wasn't considered quite as expendable as a Waco, which could fly right into a battle scenario. Shortly after war's end, American designers and military experts discussed the lessons learned from the conflict, speculating that it might be possible to land equipment without an aircraft actually landing, or at least not stopping. This idea, and other novel concepts of aerial support for ground soldiers, soon earned strong encouragement from a very qualified source, in the form of General Jim Gavin, often called the Jumping General due to his insistence on parachuting with his men in the 82nd Airborne. Gavin was a larger-than-life general who understood the needs of airborne support, and later from a post in the Pentagon championed the cause of the pod. However, the question still remained, would it even be possible for a powered aircraft to simply discharge its cargo on flyby? The Materiel Division at Wright-Patterson were given the task of finding some kind of device which could egress from a moving aircraft at a very low level. The concept of a pod began to evolve, totally self-contained and of sturdy construction. Test pods were built and vigorously tested. The main test involved pods being dropped from under the wings of a B-26 bomber, serving as a mother plane for the experiment. At first, the pods were released while the B-26 was still on the ground, taxiing at about 100 miles an hour. The results were mixed, but showed potential. However, when the pods were dropped from a mother plane in low-level flight, and out of range of propeller wash, the separation worked quite well. If these experiments could be translated into full-scale practice, then the opportunities could be limitless. The next problem was to find a suitable carrier aircraft. And here the Air Force looked to a Fairchild provider stablemate, the C-119 boxcar. The boxcar had evolved from the Packet. Both aircraft employed the same twin boomtail configuration once used on the earlier German Gotha gliders. These were purpose-built heavy transport aircraft with powerful engines. A single C-119 was totally reconfigured at Fairchild's Hagersfield plant to convey a parasite pod from one destination to another. Evolving into the XC-120 pack plane, the lower half of the boxcar was completely removed and the landing gear converted from the traditional tricycle arrangement into a quad configuration, leaving a suitable clear space to accommodate the pod. To lift the enormous loads into the air, the pack plane was equipped with two Wasp 4360 engines, which were actually more powerful than those used on the B-29. The engines provided enough power to carry Fairchild's Giant at 250 miles an hour, fully loaded. The pack plane itself had a crew of 5, 2 pilots, an engineer, and 2 especially trained loadmasters. The crew would operate a totally self-contained power hoist to upload or download the pods, and each pod had its own set of wheels to facilitate towing. Connecting the plane to the pod was achieved via 4 special clasps located on the top of each pod. Although just as important, surrounding the outer edge of the pod was an inflatable seal, driven by compressed air. This was to ensure the airflow of the speeding plane did not separate its cargo. Each pod had a drive-through layout, allowing for loading at both ends, or cargo to be driven on at one side and off at the other. Either way, it was a capacious unit, able to support 20,000 pounds of freight, or over 60 well-equipped troops. Alternately, the pod could be configured as an ambulance or a massive fuel tank. There were also plans for totally self-contained suites as workshops, headquarters, or even hospitals, all able to be delivered as complete standalone units. The pack plane, with its rapid collection and drop-off capability, provided awesome displays to the military and public alike, and possibly seemed to have had serious appeal as an acquisition to the military. And to some extent it may have, although not sufficient to gain a production contract. Only one of this remarkable aircraft was ever built, and then a few years later it was scrapped. However, if General Gavin's pod concept didn't live up entirely to his expectations, then certainly his prediction for the need of a frontline support transport with very rapid offloading did. The conflict in Vietnam provided many such uses for Lockheed's remarkable C-130, and nowhere more so than in the battle for Khe Sanh. In 1968, the North Vietnamese laid siege to an American Marine base. The objective was on a plateau in the Khe Sanh Valley in South Vietnam. Over time, the NVA surrounded the base, cutting off all land communications. Coinciding with the North's Tet Offensive on Saigon, holding the Khe Sanh base became a critical political as well as military U.S. objective. The siege lasted for almost 3 months, and for much of that time, the only way in or out was by airlift, and this was mostly achieved under heavy enemy fire. The assault transport's time had really come. Only aircraft like the C-130 and the C-123 could survive the relentless touch-and-go tactics demanded by the situation in Khe Sanh, which required rear-door delivery, sometimes speeding on the runway and sometimes over it. The determined use of American assault transport under persistent enemy fire held the line. High-speed ejection of cargo, fast turnaround, and low-level parachute drops all played their role. The U.S. had exactly the right types of aircraft at the right time. Versatile, rugged, and purpose-built for need. Things may have been very different on that plateau in Southeast Asia, without the need having been defined by the experience of men like General Gavin. In truth, the pack plane would probably never have worked well in a frontline combat situation. The demands of sophisticated and careful handling on a quiet tarmac in Hagersfield, Maryland, is very different from the mayhem of a furious battle for a Marine base in the Khe Sanh Valley. But was the pod concept really so far off? Amongst General James Gavin's other predictions was the increased need to use helicopters in modern warfare. This is the Sikorsky S-64. The civilian version is known as the Sky Crane. The S-64 was extremely successful doing recovery work and reconstruction in Vietnam. However, they also had another application of delivering purpose-built modules designed for specific functions, such as field headquarters, workshops, and hospitals. Some even called them pods.
One of the largest and mightiest transports in the world, a concentration of unusual technical solutions, and the biggest American military aircraft that has been in service for 50 years. Hello aviators, Sky here, and today we will get acquainted with the Titan that doesn't really need an introduction, and try to figure out how a military transport aircraft could become the godfather of half of modern civil aviation. Today on the runway is the Lockheed C-5 Galaxy. In the 1960s, the US military had an active presence in many locations around the world, and a rather diverse fleet of aircraft was responsible for operational logistics between those locations. The leader was the Douglas C-133 Cargo Master, a large turboprop transport capable of lifting as much as 50 tons of cargo and taking it to the right place. The plane at its time was a champion, but not without problems. It absorbed a lot of innovations, but many of the ideas of aviators were not realized in it. The turboprop engine was reliable, but limited the flight speed to 280 knots, approximately 520 kilometers per hour. Quite enough for small transports, the C-130 is proof of this, but for a long-range strategic aircraft, not so much. The military, having gained experience with various aircraft, came to the conclusion that it was time to abandon half measures and acquire jet transports. The C-135 Stratolifter appeared in the flock. Good aircraft, but limited in capabilities. Another half measure. A complete solution in 1963 was the Lockheed C-141 Starlifter. Its carrying capacity was less than that of the Cargo Master, but the speed was already decent, and its reliability and flexibility were much better. The problem was in the insufficient volume of the cargo compartment. The cost for speed was a narrow fuselage. But this satisfied the military. The C-141 didn't have to be a giant, and it successfully served in its niche for many decades. But the C-133 did not make it as a giant at all. Its advantage, the size and carrying capacity, quickly became insufficient. The equipment was getting larger and heavier. This was felt even stronger after the appearance of information about the Soviet An-22, also a turboprop but much larger. It became obvious that in order to effectively fulfill all strategic requirements, a faster, larger, and more spacious aircraft was needed. Much larger and much more spacious. The apogee of the wondering was the CX-X program, deployed back in the early 1960s, which was supposed to determine the image of a machine capable of quickly transferring to anywhere in the world practically any type of cargo. Soldiers, weapons, equipment, planes, helicopters, armored vehicles, anything. Without any reservations in the style of, this will fly and everything else takes the boat. What was this plane supposed to be like? So you understand. This is the C-141 Starlifter, a new and quite advanced aircraft. The future plane was supposed to be something like this. The guys weren't being modest, a huge cargo compartment which could accommodate more than 80 tons of cargo. At the beginning. As the concept developed, ambition and performance rapidly grew, and soon the desired payload was over 100 tons. In addition to the monstrous size of the plane, there was another, no less serious problem. The engines. The required flight speed is more than 430 knots, which means it must be a jet. Except, taking into account the size and weight, it would need 6 to 8 engines of that time under the wing, like the B-52. Terrible for a large transport. The answer to all questions was simple and colorful. There must be 4 motors. Getting them is your concern. The finale of all this research work in 1964 was the initiation of the Heavy Logistics System, or CX-HLS program. Boeing, Douglas, General Dynamics, Lockheed, and Martin Marietta, while they were still apart, took part in a tender for the creation of a new aircraft. A separate battle was fought for the engine for the future aircraft, in which Curtiss Wright, Pratt Whitney, and General Electric took part. The race was tough, and several participants dropped out of it pretty quickly. The aviators presented several rather similar solutions: high swept wings, cargo doors both in front and in the back, as well as cockpits at the top. There were also many differences, for example in the layouts of the upper decks, tail surfaces, and other nuances. During this time, Pratt Whitney and General Electric were working on the engines, and their task was just as, if not more, difficult. But they found more or less adequate solutions, which crystallized in 2 fiery hots: General Electric TF-39 and Pratt Whitney JTF-14. Thrust was achieved by using a variety of advanced solutions, both for individual elements and very large-scale ones, revolutionary for entire aviation. We will talk about them a little later. The Pentagon announced the winners of the tender in 1965. The future heavy transport would be made by the guys from Lockheed, and General Electric would supply the engine for it. This is how the Lockheed C-5 Galaxy was born. It's time to look at the outcome of this whole race. Lengths 75.3 meters, wingspan 67.9 meters, height 19.8 meters. Climbing on top of the T-tail, you find yourself on the roof of a 6-story building. Inheriting the overall look of the Starlifter, the C-5 makes it clear why it was named Galaxy. The huge fuselage is not round in cross-section, as it was done before, but resembles a pear with a wide expansion at the bottom and a narrow part above. The reason for this is the unusual layout and filling. The main element of a military transport aircraft is the cargo compartment. The dimensions were declared by the customer, who wanted to place almost the entire range of weapons here and be able to drop it on a parachute in flight. 5.8 meters wide, 4.1 meters high, and a whopping 37 meters long. It is more than the distance the Wright brothers' plane traveled on its first flight. Naturally, the deck floor is reinforced. There are fastenings for fixing cargo and equipment, as well as retractable roller lines for placing containers. You can load 6 Apache helicopters or 5 Bradley fighting vehicles or 2 Abrams tanks here. The cabin, of course, is pressurized, so soldiers can be accommodated here, up to 270 people, not counting those on the upper deck. The problem of the huge cargo compartment was access to it. One tail door is not enough, so it was decided to add another way in front. A set of hydraulic drives lifts the nose section up, and a ramp lowers below. The way through the tail is less exotic. A large flap rises at the top, a ramp lowers at the bottom, and a large double door opens in between. Plus, a vertical hermetic door inside rises to the ceiling. As a result, when all the doors are open, the cargo compartment of the C-5 turns into a huge 2-way hangar, making the loading and unloading procedures easier. Since the dimensions of the cargo compartment were fixed by the customer, and they didn't want to make the plane itself too gigantic, all the auxiliary elements were moved up, so the C-5 got a second deck stretched over the entire fuselage, like a spine. Meanwhile, the center wing box divided this deck into 2 parts. In the front is the cockpit, part of the aircraft equipment, as well as crew restrooms. In the back, behind the wing, there is a kind of passenger cabin, where in seats in the 3+3 layout, up to 80 people can be accommodated, like in a conventional airliner, except without windows. There are kitchens in both parts. Behind the passenger cabin is an extruding section with a lot of empty space called the hayloft. Here are the cargo hatch doors, service corridors, and the load-bearing structure holding the T-tail. A big thing that puts out decent loads, so there are a lot of elements. Of course, the plane is not limited to large gates. The crew will not open them for any little thing. Small doors for people are on both decks, in front and in the back on the port side, and in the back on starboard. The cockpit was made quite spacious. Here, 4 people work, 2 pilots, a flight engineer, and a navigator, in the beginning. With modifications, the navigator was no longer needed. The number of the entire crew varied quite a lot, because there are also aircraft commander, cargo operators, plus sometimes another shift. The front upper deck is designed for 15 people. The aircraft received extremely advanced flight instruments, equipped with state-of-the-art automation, navigation, and a bunch of other features, including, for example, a continuous monitoring MADAR system, with 600 sensors scattered throughout the aircraft. All critical elements are duplicated. The C-5 is equipped with 4 hydraulic systems working in parallel. The cockpit glazing is quite minimalistic. Lockheed used a scheme almost the same as that of their own C-141. The designers of the C-5 landing gear were faced with the task of making a structure capable of holding a 380-ton aircraft, not only on a concrete runway but also on grass runways. The result of their work was large, powerful, and complex. The main landing gear is equipped with 4 big legs, with bogies on which 6 wheels are installed in pairs. The pair of rear legs can rotate, which reduces the turning radius of the aircraft in a limited space of the airfield. And all these mechanics have to be closely packed inside the aircraft in flight, so when retracted, the bogies first turn 90 degrees and then go into their niches like into pockets, closed by sliding doors of large fairings. The steering nose landing gear is also not without nuance, with a single leg and a bogie with 4 wheels in a row. Meanwhile, the nose of the aircraft is narrowed, so the niche of the leg forms a small hump, and the doors do not swing open as usual, but move to the sides. In addition, the landing gear has a kneeling function. The main gear legs contract, lowering the fuselage. The front leg is partially retracted, and the plane, in a way, lies down on its belly. In this position, loading and unloading operations are greatly simplified. The landing gear does its job. The C-5 works quite efficiently in, let's say, a wide range of conditions. It took 28 large wheels for all this, but it seems to work. It even managed to fly to Antarctica. One of the most difficult tasks, which as we will see later, Lockheed solved not immediately, was the wing. The C-5 combines enormous size, equally enormous mass, and high flight speed, and aviators had to create a design that could withstand an incredible operational load. The Galaxy's wing has a span of 67.9 meters and an area of about 580 square meters, which is 2 times the wing area of the Boeing 707. In this parameter, it was second only to the Hughes' Hercules. To accomplish this task, it was necessary to apply all available technologies and solutions. The wing mechanization is highly developed. Each console has a slat extended almost to the tips. On the trailing edge, there is a group of 12 separate retractable flaps, separated by powerful drive pylons. And on top, there are also 12 spoilers, plus of course large ailerons. It looks complicated, but it was necessary for more precise control, reducing loads, and improving takeoff and landing performance. If you think that a heavy, wide-body transport the size of a building is a serious challenge, you haven't seen the engines yet. In the early 1960s, aviation jet engines were already quite decent and were actively used, with diameters up to 1.5 meters and temperatures in front of the turbine reaching as much as 900 degrees Celsius. The bypass scheme already existed, allowing a slight increase in thrust, saving fuel. The bypass ratio was about 1.4 to 1. Any engine builder of that time would say that this is quite decent. Improve the performance by 15% and there's a new generation for you. But we know what the new aircraft required, and the engine builders, seeing these requirements, decided to innovate, putting it politely. But in fact, they totally went Breaking Bad. Let's look at the General Electric TF-39. The main step towards a breakthrough in thrust was to increase the volume of air passing through the bypass duct, which became physically much larger. The challenge here was to create a much larger fan that would be capable of pulling and holding serious loads. The pressure increased even more due to the installation of the second fan. A slightly smaller one was placed in front of the main one. A bonus was the flaps along the radius of the air intake, feeding the engine at low speeds. The task was completed. The bypass ratio reached 8:1. 8. Of course, this was not enough, and almost everything was a breakthrough. The overall pressure ratio jumped from 15 for conventional engines to 25 here. Operating temperature 900 degrees Celsius, you say? Now you get 1370 degrees. This may not be very impressive in our time, but in the 1960s it was simply incredible. General Electric put all the technologies they could into the engine. The latest materials and alloys, cooled blades, sophisticated controls, everything. Thrust? The fiery heart of the C-141, the TF-33 engine, delivered just over 90 kilonewtons. The TF-39 on the C-5 was capable of 193 kilonewtons, more than twice as much. Such performance looked especially funny when the engines were passing flight tests under the wing of a flying lab based on the B-52 bomber. The Stratofortresses were mostly powered by the J-57 engines, with a thrust of 46.71 kilonewtons. And when the big guy was put in cruise mode, the aircraft could barely compensate for the thrust imbalance. In fact, it turned out that instead of 8 old engines, only 2 new ones could be installed on the plane, and the bomber would fly just fine. To the big C-5, this power plant gave exactly the performance that was needed. The aircraft had a cruising speed of around 450 knots, 850 km per hour, and a service ceiling of around 10-11 km. Average for a large jet, but certainly much better than turboprops. Considering that the landing distance of the aircraft had to be made as short as possible, the engines received a powerful cascade-type thrust reverser mechanism in the 1960s. On the ground, of course, no one wants to disturb these monsters. To provide energy at the airfield, an auxiliary power unit is used. 2 APU units are installed in fairings below, just behind the niches of the main landing gear. The C-5 is a strategic transport aircraft, and whatever its carrying capacity, it would have little use without range, which means it had to be able to fly 10 to 11,000 kilometers, or 5,500 miles across the oceans. With large loads, of course less, but not by much. With all the specific efficiency of the power plant, the appetites of the engines were huge, and there had to be a lot of fuel. 12 tanks with a total capacity of 193,600 liters were placed inside the wing, more than 150 tons. A fully equipped and fueled Boeing 757 is lighter. Moreover, the tanks are integral. There are no separate containers in them. The fuel goes straight into the internal volumes of the wing. In flight, these volumes, as fuel is consumed, are filled with nitrogen stored here. To meet strategic range requirements, the C-5 also received an aerial refueling system. It was very useful, both for increasing the flight range and for more tricky maneuvers. For example, taking off with a larger load and less fuel and adding it up in flight. Did you think only the blackbirds indulged in such things? The C-5A prototype was presented in early 1968 at the airfield of the Marietta Aircraft Factory in Georgia. A vivid impression when a building was rolled out of the building. Already in the summer, the plane made its maiden flight, and Lockheed finally entered the testing phase of their revolutionary brainchild.
120. Airborne good.
The work was carried out quite vigorously, and the first serial C-5A Galaxy began to be transferred to the military at the end of 1969. As soon as the C-5s entered service, they were immediately thrown into action. The Vietnam War was in full swing. The aircraft transported everything to Vietnam, from bullets to tanks. Despite the many difficulties in operation, the superiority over the old machines was obvious. The history of the C-133 practically ended. In 1971, they were all withdrawn from service. Alas, Vietnam did not go without losses for the C-5. During the evacuation of children from Saigon, an explosive decompression occurred on board, causing a partial loss of control. The crew turned the plane around and tried to make an emergency landing, but the plane did not reach the airbase and crashed into a field. Of the 314 people on board, 138 did not survive the fall. It was one of the worst disasters in the history of American military transport aviation. In the history of the C-5, however, it was not the only one. During the entire period of operation, 6 planes were completely destroyed, of which 4 in the 1970s, mostly without human losses. Mostly. Another large-scale transport story of those years was Operation Nickelgrass, when the group of C-5 and C-141 supplied Israel with weapons during the 1973 Yom Kippur War. At the height of the fighting, the transports carried into the country more than 22,000 tons of weapons, armored vehicles, helicopters, and planes. Given the gravity of the situation, who knows? Perhaps Israel owes its existence to this whale. Such operations, on one scale or another, were carried out by the C-5s quite actively and are still being carried out. After a couple of decades of wandering, the Pentagon nevertheless found a normal military transport. The most fun for engineers began in 1974. Remember the story about the ideas of the Soviet military to launch ballistic missiles from the An-22? Well, the Pentagon also thought about it, but these guys decided to try. The C-5, in flight over the Pacific Ocean, dropped a 39-ton Minuteman ICBM from its cargo compartment, without a warhead of course. In freefall, the missile started its engine, rose several kilometers, and then fell into the sea, completing the test. American aviators and rocket scientists came to the same conclusion as their Soviet counterparts and did not continue the work. Why did they need to launch a missile for this? Why not? Alas, the history of the big plane was not without big problems. The aircraft turned out to be incredibly complex. It was difficult to work with. There were constant problems with various systems and especially with engines. The C-5, in addition to the name Galaxy, received the nickname FRED, an acronym that stood for Fucking Ridiculous Economic Disaster. The plane was admired by everyone who worked with it, but as they say, from Galaxy to FRED, there is one step. Naturally, Lockheed tried to maintain aircraft production by finding new markets. Quite quickly, the L-500 project was born, a civilian version in cargo and passenger options, capable of carrying as many as 1,000 people. But FRED appeared for a reason, and the airlines knew about this nickname. It was obvious that such a complex aircraft in commercial aviation would be uncompetitive. And with the advent of cargo versions of the Boeing 747, this issue was basically closed. They were also actively pestering NASA with proposals to create special versions for them. In particular, it was about transport platforms for carrying oversized cargo and space shuttle orbiters. It was logical. At least one could look at colleagues from the USSR, who easily carried anything on the backs of their giants. However, it did not work out with the shuttles. NASA chose as carriers the modified Boeing 747. Yes, again. However, the agency did not completely refuse the C-5. In the early 1980s, aviators took 2 basic C-5As and, by clearing the upper deck behind the wing and replacing the tail hatch, increased the volume of the cargo compartment. This was necessary to accommodate large cargo, such as spacecraft, inside the plane. This is how a pair of C-5A SCM, Space Cargo Modified, or simply C-5C planes appeared. It was almost impossible to sell the original military transports. Although in the mid-1970s, Iran, which became the exclusive customer of the F-14 Tomcat fighters, also wanted to become the exclusive customer of the C-5 transports. Negotiations were held, but ceased after the 1979 Islamic Revolution. The world did not see a non-American Galaxy. Lockheed put a lot of effort into solving the problems of their brainchild, but when it seemed that the initial issues were resolved, new ones surfaced, which were much more difficult to handle. When it comes to advanced solutions and innovations in any complex technology, the word risk always appears. This word becomes especially dangerous when the manufacturer, for the sake of winning the tender, promises a lot of things and in a short time tries to fulfill those promises. In particular, this affected the huge wing, which they tried to make as light as possible. Composite elements, aluminum honeycomb filler, the latest alloys, as well as design optimization, a minimum of parts with minimum weight. The problem was that some of the latest solutions, due to them being the latest, were not tested that much in practice, and the optimized design left almost no margin of durability. In 1969, while the wing was tested for maximum loads, it broke, which is fine, it was broken on purpose. The problem was that it was supposed to break at 150% of the allowed maximum, but it broke at 128%. Bad sign. The second bad sign appeared during resource tests. It turned out that during active operation, fatigue cracks begin to appear in a number of elements of the wing structure, and they appear quite quickly. Lockheed came up with a plan to make minor changes that could be implemented during the maintenance process, but it turned out that they were practically useless. An especially bad part was that it all became clear when the C-5 was already mass-produced and delivered. That is, the giants already flying in the Air Force risked falling apart in flight, and in order to avoid tragic news, it was necessary to urgently limit the load, hence the performance of the aircraft. The maximum cargo weight was reduced from the promised 100 to 86 tons, and only when it was really necessary. In practice, the epic giants flew half empty. To say that the customer was unhappy is an understatement. Scandals and disputes began, up to the start of an investigation by Congress. Not only was the cost of the program well above the plan, but the resulting aircraft was far from what everyone expected. Lockheed had fallen on hard times. In 1973, after the delivery of a series of 81 aircraft, production was stopped. The financial burden of the company started to become crushing. In addition to expenses for the transport C-5, expenses for the passenger L-1011 TriStar, which had just recently taken off, were also piling up. But the company was too big to fail. The Pentagon was well aware that its bankruptcy could bring even more problems than it already has, so the government smacked Lockheed with one hand and saved it with the other. There were no options. In the late 1970s, it was decided to completely replace the wings of most aircraft with new and seriously redesigned ones, plus modify and boost the engines. Such re-winging lasted until 1986. Touch 77 planes took several years and cost about $1.5 billion, about $7 billion by modern measures. This solved the problems of the wing and restored the initial capabilities, even with a slight overfulfillment. The load capacity increased by about 9 tons. The problem was solved, but everyone had more gray hair now. Production of the C-5 was put on hold back in 1973, and many believed that after the modernization of the existing fleet, the production line would be completely closed. But history is full of surprises. After moving into the White House, the newly elected President Ronald Reagan began in his own way to revive the power of the US military. Apparently, it was weak. The C-17 Globemaster III program was still in its very early stages, while the revamped C-5 seemed to be quite decent. In addition, in the Soviet Union, its main counterpart, the heavy transport An-124 Ruslan, or the NATO name Condor, took to the skies. Being close in design, it surpassed the C-5A in a number of specifications. Those who wanted to revive and modernize the Lockheed giant received another argument in cabinet disputes. It was decided to resume production and order a new batch of upgraded C-5B transports. By the way, at the same time in the same format, the B-1B Lancer bomber received a second wind. The C-5B received improved avionics, an optimized design and updated engines. The changes were not particularly drastic, but the aircraft was much easier to operate, and the performance was again slightly increased. The load limit was now at 118 tons. The first plane entered service in 1986, and by 1989 the military received 50 units. They did not have to sit idle, because it was time for the largest mission in the history of the C-5, Desert Storm. After Saddam Hussein's attack on Kuwait, the United States and allies began moving forces to the Middle East. The group of C-5, C-141, C-130 and KC-10 aircraft delivered 534,000 people and 542,000 tons of cargo to the region in a little more than a month. Compared to that, the Berlin airlift feels like home delivery of pizza. The Flock of Giants served in this program until the end of the 1990s, when it was decided to make an upgrade. The AMP, Avionics Modernization Program, was exactly that. The C-5 fleet received new glass cockpits with digital interfaces, new navigation, autopilots, and other systems. This work was completed in 2002. In 2006, the remaining C-141 Starlifters went into retirement, replaced by the new C-17 Globemaster III. At the same time, it was decided to optimize the entire fleet of transport aircraft, and another RERP, Reliability Enhancement and Re-engineering Program, was launched, the task of which was to increase the reliability and efficiency of aircraft primarily through applying the new engines. The C-5 received General Electric F-138 GE100, which were in fact the military versions of the GE CF6 engines, which at one time were created as a civilian version of the TF-39. The circle of life. The new engine was not as exotic as its progenitor, but it was much more modern, efficient and reliable. In addition, unlike the unique base engines, the CF6, similar in components, was installed on many wide-body aircraft, making it cheaper both in production and in maintenance. The F-138s were much more powerful than the older TF-39s, putting out as much as 230 kilonewtons of thrust. This made it possible to increase the payload mass to 127 tons. Finally, a little more than that of the basic AN-124. No need to be embarrassed anymore. Equally important was the improvement of fuel efficiency, which increased the range. The new aircraft could fly 8,900 kilometers with a load of 54 tons, and empty with full tanks as much as 13,000 kilometers, nearly 7,000 miles, a quarter more than before. The takeoff and landing distances have also been seriously reduced. Now only 1,650 meters long runway is enough for work, and this is a Colossus weighing 381 tons. Thus was born the C-5M Super Galaxy version that is relevant to our time. In total, 49 version B aircraft, 2 version C and 1 version A aircraft were driven through these programs. They were already a little old and were gradually being decommissioned. By 2017, there were no C-5A left in the fleet. Deliveries of the upgraded aircraft were completed in 2018. The C-5M versions, according to various estimates, should fly for another 30 to 40 years, and will be almost as long-lived as the grandfather B-52. In total, through 2 series of production, 131 aircraft were assembled, 81 C-5A and 50 C-5B. Now in service in the C-5M version, there are about 50 gray whales. The C-5 Galaxy became a milestone in American military history and had a major impact on the world of heavy transport aircraft. But its impact on the aviation industry, although not direct, is much larger, because it is the CX HLS program that is in a sense the beginning of such a thing as a wide-body airliner. How? The aviation community was very interested in the birth of the giant aircraft. Yes, there were already large machines with wide fuselages, but it was in the process of creating a huge jet transport that the airlines watching it were convinced a plane could be much larger than what they had at that time. And what range can such an aircraft provide? What comfort and what capacity? Not to mention that this is a clear solution to the problem of overcrowded airports. Ah, how tempting. Demand creates supply. When Boeing lost the CX-HLS tender, they were immediately approached by representatives, primarily of Pan American, with the question, is it possible to create a similar large and long-range aircraft, but a civilian one? The answer to this question was the Boeing 747, the world's first wide-body airliner, which turned the entire transportation industry on its head. A queen with cult status, 50 years of serial production, and over 1,500 aircraft delivered to dozens of airlines, against 131 aircraft supplied by Lockheed to the military. This is what you can do with the ability to overturn even a defeat. And this is just the 747. The rest followed. DC-10 and L-1011 in the USA, in Europe the A300 was born, the first Airbus, and in the USSR the Il-86, and all within literally 5 to 6 years. It is quite difficult to imagine the modern air transportation industry without wide-body airliners, and all the current big guys, one way or another, came from the desire to stuff a couple of tanks into a plane. And the second innovation that has affected the industry practically on a total scale is engines. When the C-5 was created, it required a power plant that combined huge power and decent economy. To meet this requirement, engine builders made a real breakthrough by creating the world's first large turbofan engines. The TF-39 won the tender and took to the wing, but General Electric could not deny themselves the pleasure of creating its civilian modification. And so, the GE CF-6 was born. The losers of the tender, Pratt & Whitney, just like Boeing, did not lose heart, and putting away the military JT-F-14 made a civilian version on its basis. This is how the JT-9D engine appeared. This company was a huge breakthrough in civil engine building and the key to wide-body aviation. Without them, such large aircraft simply wouldn't be able to fly. It was they who became the basis of the fiery hearts of most early wide-body planes, and it is their concept and solutions that are the basis of civilian jet engines to this day. The history of Galaxy began half a century ago and will continue for several more decades. The epic nature of this giant is hard to overestimate, as is its impact on the aviation industry. Let's wish good luck to the gray whale, and hope that it will not have to fly to hot spots with tanks in its belly. At least not too often. And this is where our story ends. Like and subscribe to the channel so as not to miss the continuation of the great transport saga. And if you want to watch the videos early, see some exclusive behind-the-scenes content, or just support the channel, consider joining our Patreon community. Fast flights on large planes and soft landings to you.